let's start. Thanks for sticking with me. Thanks for coming here in the afternoon. My name is Francke, so I'm also a member of University of Potsdam, and I have the pleasure to conduct with you here in the afternoon some exercises on river discharge measurement and their related analysis. So probably if you remember what Wolfgang showed during the introduction. So basically, we've been listening to some introductory lessons that I cannot provide to you once more, but sorry about it. But mainly the things that I will be presenting are relatively basic. If they are not familiar to you, there will be a PDF where you can look up some of the background information that's necessary. During the past week, we've been out in the field and doing some measurements. And basically, the idea is to use the data that we acquired during these days and do some analysis on them. It's some very basic stuff. Probably if it's too easy for some of you, I apologize, but I hope there will be something new for every one of us. So that means we are in the final part 3, so the data post-processing, and we will do so exclusively with using R, the open software R. I hope you have downloaded it. Otherwise, please do so. It's not as massive as MATLAB, so it can still be done within a couple of minutes, I guess. So that means our goal for this afternoon is to fresh up some of the methodological background on these discharge measurements, look at the actual fieldwork data that we've acquired, and well, do some exercises on programming. Everything is still quite, I think, basic in terms of the programming requirement, but if you are probably new to R, it may also provide some kind of insight into how this language is working and probably what option it provides for you. So with that said, I'd like to know who of you has any background or experience in any type of programming, and to survey that, I'd like to ask you to give your answer on this website. So there's a code that you can scan, or alternatively go to this URL menti.com and enter the code that's written here. And I'd like to know from you, okay, which are the programming language that you are familiar with, that you have used, that you would use for any task you tackle, if any. So let's give me some insight on your background, please. Okay, thanks. We don't need to go that deep. It's no scientific data acquisition here. Just for a flashlight. Okay, it seems like most of you are preferring Python, MATLAB or Scilab Octave as a runner-up here. So that means most of you will be familiar to this kind of interpreter languages, which is nice. So some of you have worked with R as well, but I think for the others it will not be too much of difficulties using it. I just saw that I didn't provide the answer option of using none. Okay, but I think since this is a technical university, I think most of you will in some way or the others have used some kind of programming language. Okay. So for those who have ever worked with R, can I just give us a few insights on how familiar you are with it? For those who have not been in touch with it, well, you can still say, okay, I never used it. Okay, thanks. I think that will do. So that means, well, I think there is some need that we look at some of the basics so that you can enjoy the exercise to its full extent. So I will start with some very brief introduction so that you just get some ideas on the syntax and how to use it. So basically, we will only use very simple commands, but for that, I will provide just some kickstart to get that. Okay. So basically, these are the tasks that I'd like to tackle with you. We are focusing on those black listed bullet points. The gray ones are still contained in the results that you can download. If you're very eager and ambitious, you can look at them as well, but we will only look at number 2, number 4, and number 6, which should be our main focus. And I'd like to ask you to download the data and the templates, which will also contain some introductory lesson that we will do together. And after that, I'd like you to tackle these tasks by yourself. So we will take some time and we try to see how much we can solve. It's not about everyone doing all of the tasks, but sorry about it. But try to find whatever you are most interested in. I will try to go between here the aisles and help you out. So it's more about you getting the hang of it and trying to figure out how things work. And you can also progress your or you document your progress on this other website so that we have an impression of how far you have come so far. Okay, so that means right now, please download the data that you will find at this URL. It will lead you to some structure of some directory structure, and we're gonna start with number 0, which will be the introductory thing. I will do so here at the screen as well, so you can follow my actions then. So please, if you have entered that URL, it should lead you to this directory tree, and we'll start with number 0 into 2R. So there's 3 files in there. Please download them and save them to your local storage. So after having done so, you can just double-click on this R file with the extension .r, quick start, and RStudio should open, and it should look like that. So we need all of the files that are located in that folder 0_intro to R. Okay, so this is the IDE that we will be using. So it's pretty much similar to the IDEs you may be comfortable with, be it Eclipse or Spider or PyCharm or whatever you've been using so far. So it consists of a section here in the upper left, which contains our script, which we can then save as a basic plain text file. We have some console array here in the lower left, so that's the actual engine that's running our entire thing. There's a place here which shows our current objects in our workspace. Here's an area where plots will pop up, or we can also get some help. So if you have opened this file, quickstart.r, it just contains some basic examples of things that we will need during our exercise. So you can always have a peek there if you get stuck. So let's briefly walk through this. So you can see there's a special command char, which is being used to denote commands in the code. They are not being processed, and also highlighted here in green, whereas the actual code is written in some other colors. So let's start with a simple assignment, which is x is 3. So you can do it like that by just typing it down here in the console window, and it will show up here in your workspace. Likewise, if we type it up in here, it's not being processed yet, but instead we can run this single line by just pressing the button here on top. Same goes if you press Control and return, which processes the current line, so this might be quite handy. So I will briefly go through this script here now by just pressing Control-Enter. You can do so likewise and also modify the commands if you want. If there's any question, please do not hesitate to interrupt me, and we try to sort out if there are any things that you need to know. So if you're more familiar with using the equal sign, which I find a little bit easier to read, you can use it as well. If you just want to print the value, well, surprise, it's just by entering the specific entity or using the print command. So again, we should see the results here in the same way. Of course, we can do some math. So this is just some computations here, which uses the square and some addition here, and we again check the results. So this is just the assignment. We do not see the result yet. But if we process the next line again, we see the results. As for next, we can also use vectors. They are assigned in a way like that. So the vector containing the numbers from 1 to 5 would be defined in this way. We can also create more complicated sequences using the command in line 25, which defines a sequence starting from 2 going to 10 with an increment of 2. So if I execute that one, I will get this series of 2, 4, 6, 10, 2, 4, 6, 8, 10. So having these respective numbers created. To access a single element of a vector also works similar to other scripting languages with these square brackets. Please remember that indexing starts with 1, so opposed to Python or I think MATLAB as well. No? Okay, to Fortran. So they start with the zeros. Here it's with 1. So that means we have some options here now to deal with some of these vectors and arrays. So that means we also need probably to concatenate some vectors, which can be done with this command, brief command, just C. So concatenate connects two vectors and ties one to the other. So we have the first vector that we created and the other one appended to that one. Any questions so far? So there's vector math that we can do. So by simply adding 1 to every single element of the vector, we can add 2 vectors if they have the same length. So that's all very obvious, I think. And can also do some like aggregating operations on these vectors, like computing the sum, the mean, the max, or whatever. For any of these functions that are implemented in R, we can easily get some help by using this command, so the question mark and the respective command. Same goes if I place the cursor on one of these commands and press F1. So we will get some help here in the lower right window, which always provides the explanation how this function works, what it does, and also some examples. If you scroll down to the lower section of the help files, there will always be some examples how to use it. So you can easily build on these examples and modify them if you want to adjust your own needs. So science is all about sexy pictures. So that means if we got some data having processed, we'd certainly like to visualize it. So this is the simple plot to fill, which plots command, which plots one of these vectors that we defined against the other. So pretty straightforward and simple. Of course, there are plenty of other more complicated ways of displaying data. But for today, I think these kind of plots will mostly suffice for our purpose. So that means plotting, simple plotting, probably adding some lines to that, and a legend if it need be. Any questions so far? Okay, that's all pretty obvious, I think. Now what we will definitely need is to import some of the data that we measured. So there's one command that we will need for that purpose, which imports text data, which is called read.table, so basically tabular data from text files. And this is done with that command here in line 54. And now we see that there's a new object here that turned up in the workspace, which is exactly this, what we call it, a table. So we can click on this one and see that it's a table with 4 different columns. You can also double click it and see what the contents of this table is. So this is one of the files that you should have downloaded beforehand. So it's exactly this one here, data table. So if I open that in an ordinary text editor, that's exactly what we have imported into R. So again, so this table also offers some options to access the data within it. So we can get a single column like this one, which contains some string information, or we can likewise address this column using numeric indices. So this basically here, this section translates to give me all lines, all means that this is like an empty space, but the first column. So it's rows and column. If I would need a specific row, say the second row and the first column, that would work like that. Same goes for, removing these columns or creating new ones, so we can just make up a new name. Let's say our knowledge we can discard, and after this afternoon, probably all of your knowledge has been not completely replaced by absolutely high values, but at least your desire to know more about it should have increased, hopefully. So now this command created a new column here with the respectively named field. So this data, of course, can also be plotted here, and you see again like a simple scatter plot that we will be using quite often today. After all, we can also export these data again, write it to a text file in the same fashion. We can provide the separating character that we want to use for that purpose, and the respective command is write table. So this should create a new file in your working directory then. Any questions? So the last things that we will need are how do these program control structures work. They are pretty much alike to any other programming languages that we've mentioned before. So what we can have is like conditional clauses. So let's say we have got an animal and want to know which sound it makes. Well, we can check if it's a cat, the sound is meow, otherwise it's a different sound. So that would like this one here in R. So again, the condition is put here after the if in these braces, and then we have if a command if the condition is met, otherwise if the condition is not met. So pretty much similar to other scripting languages. If you want to imply several commands, you can embrace them or combine them with these curly braces that would look like this one. So now we can accommodate multiple commands within one of these blocks. So let's say the cat, what other sounds do cats make? I don't know. Yeah, I don't know, how would you spell that? I don't know, probably like that. Not sure if the cats would agree. Okay, so this one goes here in the same line. So now our cat should make two different sounds as well. So it's not only pleased, but also annoyed, apparently. Okay, so this is for conditional clauses. For using loops, like in other languages, we have the for and the while loop, both similar to other languages. So here we have some counter, counting 1 to 10, pretty obvious. I don't think I need to tell you more about that. And while condition, so we can like mimic a countdown here, which of course could also be implemented with the for loop, but just for the sake of it, we can use while and a condition that breaks the loop. Okay, any questions so far? No, I think this is all pretty obvious. Yeah, I think this is just as much as we need for today, so pretty basic programming structures. I just wanted you to give you this template so you can briefly look up stuff that you will need to tackle the respective tasks now to come. Questions? Nope, none. So then let me skip back to the actual task. I'll briefly again summarize what the actual purpose is. So let's start with number 2. So this is the dilution-based measurement that we conducted in one of the streams. So that means we used some tracer. In this case, we used, in the first attempt, some fluorescent dye, which has been placed into the stream where it was mixed and diluted, and further downstream we mixed its concentration and the respective breakthrough curve over time. And this curve contains some information on how much water is there in the channel. We repeated the same measurement also with a simple salt tracer, so just salt being introduced and measuring the conductivity respectively. So the idea is the same, the data is different. So both data sets are contained, and now your task is use these data, which we downloaded from the devices, and compute the respective discharge. The background for this one is also given on the introductory slides on page 11. So you will find these slides also in this file structure here. So they should be somewhere down here. Yeah, so these are the slides for the introductory lecture that I gave that unfortunately you missed. Any questions regarding that task? No? Okay. Let's look at task number 4. What we did is measuring discharge for different water stage levels. So basically what you see here. So that means we have a section where we measure repeatedly the discharge for different runoff conditions, and in the end what we would like to have is some kind of relationship to relate the stage and the discharge values. So the more we have, obviously, the better our relation can be confined. And this is just a very simple example where we have some data points, and what we would like to do is fit a power law to this kind of data, which then again allows us to use a continuous series of stage measurement. So there would be a stage recorder permanently installed within the river, which would create a time series of these stage values. And by applying this conversion function, we can convert this into a continuous series of discharge values. So this typical way of how discharge is being measured continuously. So that would be task 4. Any questions? Okay, and finally, a little similar task. So we measured suspended sediment concentration. So that means how much sediment is there in the river being transported in suspension for different discharge values. So it looks pretty much alike. And this is the way that's often being used to construct sediment fluxes or sediment budgets from catchments. So that means because we cannot as easily measure sediment flux or sediment concentration continuously, we are using the discharge as a substitute, which is more easy to measure continuously. And we use this conversion function, so this is a very easy, simple approach, to get a continuous series of the concentrations. Then again, if we know the concentrations and the discharge, we could also integrate this over time and get some estimates on the sediment yield. So that means how much sediment has been exported from the catchment over a certain amount of time. So again, there's some example data on these, and you're supposed to fit this line and apply it to the respective discharge data. So these are the 3 different tasks that I want to tackle with you. There's another link there, I already showed it, where all the solutions are contained. But of course, the idea is not that you look up the solutions right now. You can, of course, do it in the end. But now rather form teams, whatever, or do it on yourself, whichever you prefer. And choose those things that you're most interested in. And let's see how far we can get. I will try to answer your questions meanwhile and come to you whenever you are stuck. So please don't hesitate to give me a yell whenever there's something that you need to know. Okay? So let's again briefly look at the results. So starting with the dilution experiment, you should have got something like these data having imported. So this is the relationship between the conductivity that has been measured by the sensor and the concentration that we established in our solutions, so an on-site calibration that we performed. So, and we fitted this line through these data here to get the respective coefficients. And obviously these points more or less are aligned very closely along that line, so that linear relationship between conductivity and concentration is quite well established there. After that, you hopefully succeeded in importing the data. So the original raw data is the time series of conductivity, which then has been converted using the regression coefficients into a time series of concentration. So, and as you see here, this is the typical shape of this breakthrough curve, a bell-shaped curve that is slanted towards, because the washing, dilution of the tracer out of the river reach, it takes a little bit longer than the first parts to reach. As you may have noticed here, there's a slight offset between zero concentration and the concentration we get from our conversion. So this is apparently because the background concentration in the river was slightly different from what we measured in the calibration vessel. This may occur when our calibration vessel is somewhat contaminated because from prior experiments or because we took too long and the temperature changed a bit. So to account for that, I just shifted the curve upwards because we are more interested in the relative changes than the absolute one. So we can just shift the curve by this minimum offset, which look like that, and which then allows us to compute the discharge. In this case, I think it's example number 1. No, it's example number 2. The total discharge was 102 liters per second. So relatively small stream that we conducted the experiment in. So then let's proceed to task 4, the rating curve. Again, here you had to import some data. I need to change the working directory now because we're in a different one. And it should look a little bit like that in this case. So that means 4 different water stages, in this case for water stage 91.3, for water stage 91.7, and for water stage 91.9, we have respective measurements. So that means we did 3 different measurements on 3 points in time, and each time we had 2 sensors in the water which yielded 2 results, 2 discharge rates. And if we would now try to establish a relationship between those 2 entities, between stage and discharge, it would look like this. Not very much like a power law, but in this case, quite linear. So what do you think, what could we criticize about this situation here? Well, probably that gets clearer if I proceed. I use this relationship here now to convert the measured stage values. So these are the stage values that we measured during our field trip over a certain amount of time. In this case, it was just 1.5 days. And so the stage in this small river varied between 80 centimeters, so it was in a relatively deep pool, mainly reached around 1 meter, and for some very short occasions had these peaks up to 1 meter and 30. So I use the equation that we established before. So here from this graph, I can convert these water stages into values of discharge, which looks like that. So what would be your comment on this outcome? It's quite some heavy floods indeed. I mean, probably, well, you have not been there, you have not seen this. It was a quite small river, probably the size of 1 meter. And here, this result implies that we had some peak discharge values of almost 8 cubic meters per second, 8,000 liters per second. So this is clearly not plausible. What do you think could be the reason that we get these implausible values here? Well, the reason is to be found in our discharge stage relationship. So as you can see here, we had measurements covering the stage values ranging between 91 and basically 92 centimeters. That means, looking at this graph, we have some data here within that range only. And the proper discharge here for stages of 130 centimeters, we never measured. So we're just extrapolating our curve that we get here. So this one, we're extrapolating that curve until 130 centimeters. And this is quite a common situation in permanently set up gauges, that we are interested in the floods, but we do not have any data there. So what we do is extrapolate our curve. This is a particularly severe example because our data is really scarce here. I mean, 3 measurements is not overly impressive, but still, if we had many more in the lower ranges, we would need to extrapolate for the further water stages that are well beyond like the regular water flow regime. And this is always the part of the hydrograph which is most uncertain. So that means if we want to establish a proper discharge rate in the upper range, we have the highest uncertainty there. And this applies basically to all stream gauges that are being run, because during the high stages, usually no one is there, they are very short, it's dangerous to go in the water, there's too much debris in there, whatever. So this is always affected with a lot of uncertainty, and especially here, we have to admit that this stage discharge relationship is quite poorly confined, and we should not use this for these high stages. So that means go there, collect more data during these high stages, or apply more sophisticated approaches. There are other ones that can also use the cross-section to get at least more reasonable estimates for this extrapolation. But in this case, using only 3 points of data is clearly not sufficient. There's another file in here which uses more data, so they can also use it for like more reasonable data situation. But I wanted to have this as an example, as like a poor practice example. Procedure number 5, so the last one was about the sediment rating curve. So the idea was that we have some data on sediment concentration and the corresponding discharge values. So this is how our data looks like. So that means here the data situation looks much better, so approximately 20 values of discharge and the corresponding sediment concentration. So how is sediment concentration usually being obtained in a case like that? How would you do that? If I ask you, this is my river, the discharge now is 20 cubic meters per second, what's the sediment concentration? How could I do that? Well, go out and sample. Take a sample of water, take it to the lab, filter it, dry it, and see how much sediment you will find. So basically that's the concentration amount of sediment mass that you find in these cloudy waters. So that has been done here for 20 times. So this is time consuming because you need to go there, you need to be there in the spot when the discharge is high, of course, because this is most commonly the situation that we are most interested in, because the concentrations tend to be much higher during higher discharge. So that there's much work involved into these kind of things, obviously. But if we have these data, then we can see that there's this relationship between discharge and sediment concentration, and we can fit this line. So usually it's a power law, and we can use this line like we did also for the stage discharge relationship to convert our continuous series, which in this case is discharge. So we have a time series of discharge here starting from July or June till the beginning of September. So this is a catchment that's mainly active during that time. Before that it's frozen, after that it's frozen again. So we can use these discharge values then using the rating curve and create a corresponding curve of sediment concentrations, because measuring sediment concentrations continuously is even more exhaustive and more complicated. There are ways to do that, but the equipment is more expensive, it's more prone to failure. So that is why this is a very common approach to do. So for this example, we would see, okay, mainly the concentration is very low. So these are like base flow conditions. There's almost no sediment concentration to be discerned here, whereas there are some couple of events that produce very high concentrations of up to 60, 70 grams of sediment per liter. And if we would like to integrate this over the entire season, that means we compute the total amount of sediment that is being exported from the catchment. We would use the series of discharge, the series of concentration, multiply them, and get a total amount of sediment that has been exported from the catchment. Usually this amount is then again put into relation to the size of the catchment, because obviously if you have a larger catchment, then you get more sediments. And so a specific value would mean we get a certain amount of sediment per unit area. In this case, the example here would yield something like, I don't know, let's see, almost 2,000 tons per square kilometer. This is a comparatively high value, but it's still quite reasonable for alpine catchments that are glaciated, because commonly the glacier create a lot of sediments because of their geomorphic activity. Okay, any questions regarding sediment rating curve? Probably as a side note, so this strong or this very obvious relationship between discharge and sediment concentration is not always the case. So the more complicated the geomorphological regime becomes, the more dispersed this may be. So sometimes like the seasonality plays a role, sometimes the rainfall plays a role, the temperature may play a role. So if things get complicated, these like nicely aligned dots may somehow scatter more and more, and there may be no real relationship or direct relationship with discharge. There are other more sophisticated approaches for doing that use multiple variables, like all these predictors that I mentioned, and more intricate techniques that can be used for regression, like multivariate regressions or tree-based regression approaches that can also cope with these kind of situations. Okay, so this brings me to a close. So what we have accomplished, I think, is quite agreeable, so that most of you have done at least one task. Some have probably two or three. You can use also so in the end, on these slides, there's a URL that provides also a link to those solutions, so we can look at these again. So if you one day, I don't know, decide to do something on your own, you can use your solutions or these to start from. In the end, still, I want to briefly mention a short discussion that we had during the days when we were out there in the field. So the question is, okay, why do we still need these kind of things to be done? I mean, who's interested in discharge? Of course, well, it's a useful value, but I mean, we can use it from data sources. We can download it from the internet, or we can use satellite products to estimate sediment concentrations. So why is there the need to go into the field? And the answer to that is that, of course, these like remote sensing-based approaches or model-based approaches get better and better. Whenever you look at one of these really precisely, you will find, okay, the baseline is still measurements, is still proper data, going out there and assessing how good our product is. So that means do not like blindly trust anything that is being done on a large scale in a very broad coarse resolution, whatever. But fieldwork data is still precious. There's a lot of effort in there, but still this is the ultimate truth, that we need to compare our other results against this. So this is a strong like encouragement to think about fieldwork data and also to appreciate its value. And with that, I'd like to thank you for your attention and have a nice afternoon.